Good evening, everyone. I hope you are doing great. We are going to continue. If you remember, we went all the way to the end of page 103. We start a new topic, which we already work on it, but we are going to work specifically on overfitting and underfitting. You remember in the previous chapter 3, we worked on IMDb, which was a binary classification, and after that we worked on the Reuters, and it was a multi-class classification, and finally we worked on the Boston housing, which was a regression. In all of this, after just first or second epoch, we saw that we started feeling overfitting just quickly after a few epochs. What does it mean, overfitting? Means that you remember something like this. Means with the data in hand, we get lower and lower loss, while after a few epochs, we saw that the pattern or the patterns that we learn in the data in hand would not be very much general. So they are very much specific to the pattern that we have in the data in hand and not on scene data or validation data in this case. After a few epochs, you see that it goes a little bit better and better in unseen data as well. But there was a point that right after that, we have worse results in the unseen data while we get better and better in data in hand. Guys, does it have any value to get the best result with data in hand while we deteriorate the results that we have in unseen data? Yes or no, true or false? Is it valuable? Guys, yes or no? It's not a trick question. Is it our goal to know what are the labels for data in hand? You already have that, those labels, right? You already have that information. So what is the point? So if you make the model perfect with data in hand, what's the big deal? You already have the labels, but you need to see if your model works almost similarly with unseen data. So you see that in epoch number 7 is the part that we have to stop, right? So it says that the fundamental issue in machine learning is the tension between optimization and generalization. What are optimization and generalization? Optimization means you make your model work, that you make it work the best with data in hand and find as much as patterns that you can just find in the data. But the generalization means that your model become in a format that it works similarly with unseen data, right? Technically, the training data set is working to improve the optimization. Look at this one. It says that optimization refers to the process of adjusting a model, means adjusting weights and biases, to get the best performance possible on the training data, and the learning in the machine learning. Whereas generalization refers to how well the trained model, you already trained it and you just apply it to, what do we call it? To validation data, which is gonna work like unseen data in this scenario. On data it has never seen before. The goal of the game is to get good generalization, of course, but you don't control generalization, and that's the problem, right? We don't have any control on unseen data. We can just adjust the system based on the data in hand. So how could we relate these two? Look at here. The optimization and generalization both works in the same direction up to this point, but after that, still we have better optimization but we have worse, is going to stall or even worsen after epoch number 7. Guys, there's one good news. If you just collaborate and talk and say the answers, we're gonna just finish it as soon as possible. So let's just have that communication. So do you see that we go the same way, the same approach all the way to epoch number 7? Means that we have progress in both optimization and generalization. And that is the time that we have underfitting, means that we can get better and better, right? We have underfitting. If it is clear, please type 1. Thank you, Algor. Erdal, merci. Anand, thank you. And look at this one. After that, we are going to have worse generalization, but we improve our optimization. It's which is going to be the overfitting part. It says that at the beginning of training, optimization and generalization are correlated. The lower the loss on trained data, the lower the loss on, well, guys, it says test data, but in this scenario, what is it? Validation. While this is happening, your model is said to be underfit. There is still progress to be made, and the network hasn't yet modeled all relevant patterns in the training data. But after a certain number of iterations, epochs, on the training data, generalization stops improving and validation metrics stall and then begin to degrade, right? The model is starting to overfit. So when they go 2 different roads, 2 different directions, then we say that they are feeling overfitting, right? That is the beginning to learn patterns that are specific to data in hand, but not general. So they are going to be misleading or irrelevant when it comes to new data. Hi, Donald. Good afternoon. So look at this one. One solution to overcome overfitting is to prevent a model from learning misleading. What does it mean to prevent, guys? The very first thing that comes to our mind for overcoming the overfitting is feed your training with huge number of samples, as much as you can. So the more samples that you have, the more general the model could be. It's very intuitive, right? Because generalization means that how your model works with more number of samples, right? How it could cope with more number of scenarios. So the more it says that a model trained on more data will naturally generalize better. No need to explanation. But what if you're not capable of doing that? Okay, can I have everybody's attention if everybody is at the system, not cooking or eating? Please type 3. Lovely, Algor, merci. Sabrine, hey Sabrine, how are you? Erdal, bravo. Guys, what if I ask the system, please focus on the patterns that are more general? In that case, you need to decrease the number of neurons and layers. Means, hey, we don't have that much resources, right? Just focus on the most important thing. Guys, does that make sense? Yes or no? Whenever you have less number of I'm sorry. Whenever you have less number of hyperparameters, in that case, you're going to do what? You're going to focus on the patterns that are essential. Look at this one. If a network can only afford to memorize a small number of patterns, the optimization process will force it to focus on the most prominent patterns, which have a better chance of generalization, right? Which have better chance of generalizing well. The processing of fighting overfitting this way is called regularization. One of the ways is lowering down the number of layers and neurons in each layer. Absolutely correct. That is one approach. What could be the other approaches? These are the things that we are going to learn. We just talked about one of the possibilities, which is lowering down the architecture in terms of hyperparameters, or we are going to see another name for it in a few seconds. They call it capacity of the network. Okay. May I have your attention, please? It says that reducing the network size, this is the simplest way to prevent overfitting, is to reduce the size of the model, the number of learnable parameters. Guys, what did we call learnable parameters in the model? Which determined by the number of layers and number of units per layer. Guys, what was the other name that we used always for this? Lovely, hyperparameters. Exactly, Al Gore. Look, the other name that we see here is in deep learning, the number of learnable parameters in a model is often referred to as the model's capacity, or as Al Gore said, hyperparameters. Intuitively, a model with more parameters have more memorization capacity, and therefore can easily learn a perfect dictionary-like mapping training samples and their targets. What does it mean? Look at this one. Imagine that we have our beloved example MList. I'm going to bring it to you here. And okay. Imagine that we have, guys, how many parameters you see we have here? We have two, in this two example, we have two hidden layers, and in each hidden layer we have just 16, which is going to make it 32. So from the input all the way to output, we could have 32 parameters like that, right? Does that make sense? But what if instead of that, I have something crazy like 500,000 parameters, right? Isn't it going to be crazy? Yeah, as beautifully both our team members said, Al Gore said, it will generalize too well if you have huge number of parameters, and it will go from learning to memorizing. Why? Al Gore, why we say that? Can you please elaborate more for the audience? And feel free to pick the mic and talk to friends.
Yeah, I think that it won't be learning, but it will just memorize the patterns so that when you ingest an input, it will just look for the pattern instead of looking for a kind of learning pattern. It will be like memorization instead.
Sure. The reason for that is, imagine that this is our handwritten digit. This is one. How many samples did we have? We had 60,000. The book said wrongly that we have 50,000. Let's just think that we have 50,000. In that case, we have 50,000 samples. Imagine that. The last one is 7. The first one is 1, for example, right? So for this one, guys, we have 10 different neurons. Look at this one, 500, sorry, 1,000 divided by 50 500,000 samples, it means that for every single picture, we have 10 neurons. Does that make sense? Anand said over fitting, because it's expensive lookup table, lovely. That's what I wanted to say. We have 10 digits here. It's like 0, 0, 1, 1, 0, 1, 1, 0, 1. So when you see such a thing, it's going to go to a kind of 10-digit code, because I didn't count that it is 10 or not, and it goes to number 1 here. And if you just have 1 tilted a little bit, and there's no guarantee that it can recognize that, because you have just personalized, specialized this picture to get to the result with this series of numbers. It's like decoding specifically. So it's not going to find a pattern. It's going to be a kind of, as Anand said, expensive lookup table. And let's see what the book said about this. As actually all of you said correctly, therefore, intuitively, a model with more parameters has more memorization capacity, and therefore can easily learn a perfect dictionary-like mapping between training samples and their targets. And mapping without any generalization power means if you see a new one, there's no guarantee that you can recognize what is happening, what is the pattern. For instance, a model with 500,000 binary parameters could easily be made to learn the class of every digit in MNIST training set. Well, with a little bit of compromise, we could say that we would need only 10 binary parameters for each of 50,000 digits. But such a model would be useless for classifying new digit samples. Always keep this in mind. Deep learning models tend to be good at fitting to the training data. That is what we call it optimization. But is this the goal of having machine learning and deep learning? No. We want to use it to find patterns between unseen data sets, right? The real challenge is generalization and not fitting. You use fitting to see what could be the best model, right? So everything is clear so far? If yes, please type 1. Oh no. And merci. Parsa, thank you. Okay, let's go. Guys, is there any question, anything which is not super clear? Donald? Donald is in a lineup to get ice cap, I guess. Okay, let's go to the next part. On the other hand, if the network has limited memorization resources, what does it mean? Guys, if you do not have enough number of neurons and layers, you are gonna underfit. It takes longer to get a proper classification. Does that make sense? Anand, is it clear? If we have, instead of, for instance, let me just go to this example. Control V. Okay. If instead of having 16 neurons here, which is the default that we had, we use just 4, what's going to happen? Albert, what's going to happen? Is it going to find the pattern at all? Yes or no? Well, what about this? Finding, no, I don't think it will be able to. What about this? It takes more time and it's going to focus. You remember that it says that if you have not enough resources, we are going to focus on just look at this one that we said a few seconds ago. And therefore, we can learn, oh, I'm sorry, not here. It says that if a network can only afford to memorize a small number of patterns, the optimization process will force it to focus on the most prominent patterns. So it is going to work on the very important pattern or very important patterns, which have a better chance of generalizing. Well, do you remember that? So first, it takes more time and it just focuses on the most important patterns. So deep learning models tend to, okay, we talked that. How about this? You should use models that have enough parameters, not too much, not enough capacity. So we should find a kind of trade-off between too much and too few, right? You should use models that have enough parameters that they do not underfit, while at the same time not overfit. There is a compromise to be found between too much capacity and not enough capacity. Unfortunately, there is not a magical formula to determine the right number of I'm sorry, of layer or the right size for each layer. So we can think of something like, how about this? Let's have a for loop for number of layers. Guys, it's a pseudocode from zero, not from zero, definitely not zero, sorry. From, for instance, 1 to, I don't know, 100. And then we are going to have another for a number of neurons from 16 to Can I move you, please? Okay. Okay. I just want to say here, what a beautiful handwriting. I think that I can write better with mouse. For neurons, which they start from 16 all the way to, for instance, 512. And the way that we add it, we're going to say it is neuron is equal to neuron plus or double, sorry, multiply 2. Let's say neuron times equal to 2 means that it's going to be 16 first, then it's going to be 32, then it's going to be 64, 128, 256, and 512, right? That kind of thing. Why we are going to do that? These are the numbers that they can easily fit in the GPU. That's one reason. And guys, we start from low numbers like 1 layer and then check all those things and then we increase. If we go the other way around, if you start from 100 and then we go back to 1, it takes forever. You know what I'm saying? Because after a while, for instance, after you get to, I don't know, 10 as the number of layers, maybe you see that, it takes so many hours to finish the job. So you're going to say, you know what? That's enough. I'm not gonna go any further. Does that make sense, guys? So we start from low to high. Look at the things that the book said in here. It says that there is no magical formula to determine the right number of layers or the right size for each layer. You must evaluate an array of, you see that I created that array of different architecture on your validation set, not on your test set for sure, to find the correct model size for your data. The general workflow to find an appropriate model size is to start with relatively few layers and parameters and increase the size of the layers or add new layers. Guys, is this one clear after showing you this kind of nested loop that we create a matrix of possibilities? And we are gonna, for each of them, for instance, you're gonna write, okay, when I have one layer and 16, the validation score that I'm gonna have is going to be x1. And then when I have 132, the validation is gonna be x2. And then after that, you're gonna say 2 when I have 16 and 16, the validation score would be this one, and so on and so forth. So you're gonna have a matrix to determine which one works the best. So let's just have an experiment. This is the standard 16, that is to go for MNIST. Let's just consider that we use the same architecture 16 for the IMDb, which we had the most 10,000 most frequently used 10,000 words. And let's go to this side of the extreme and bring it to 4. Right? You do remember the information bottleneck? Right? Okay, let's see if you go to that side of the extreme, this is going to be the result. The plus signs are the regular 16 and 16, and these blue dots would be the smaller, which is going to be 4 and 4. What can you understand? Please just spend a few seconds. Anybody who's volunteering, you can pick the mic and start explaining. What do you understand from this picture?
Can I answer?
By all means, yes, Anand, thank you.
To me, it looks like the um, original model with more layers. It looks like it starts overfitting a little bit earlier. As we can see, the validation loss starts increasing at about 2.6. And if we look at the smaller model, it increases maybe around 5.8 or something like that, 6 or so. So it takes more epochs. It can run through more training data before it starts overfitting.
That's perfect. Lovely, Anna. Can we say that here in this example, we get to overfitting when we have smaller model? We get to overfitting after 6 epochs because this is 1, 2, it should be 3, 4, and 5. So we get to overfitting after 6 epochs, and the trend is way smoother and predictable. While when we have 16 number of neurons in each layer, we have something very noisy, as you see, and we suddenly get to overfitting, right? After just 3 epochs, we faced overfitting, and then the noise is not, it's not very smooth, it's very noisy and very spontaneous, like up, down, and not very crazy, but we don't have the smoothness that we can see in this approach. True or false? Is it correct? Let me just write. I love this group. People actively. Let me just write the names so I can appreciate at the end of it. Okay, Anand, do you accept what I said? Are you okay with that? Okay, sorry. Al Gore as well. So Al Gore, let's go to the other side of the extreme. Guys, I just said Al Gore. If anybody else wants to step in, feel free to just raise your hand or just say, I want to step in, right? And the question that I have for you is this. What if we go to something crazy like 512? Look at the result. Do you see that that is the original? And that is the crazy, like here. Do you see that how noisy it is? What can we understand? What can we understand from this? Parsa, do you want to step in? If you have mic by any chance? Or if you're in a place that you can open your mic. Guys, if you don't know the answer, don't worry, I can ask Donald. Donald. Yes, Albert, please.
Yeah, so for this graph, we can see that for the original model, it starts overfitting right after 2.5. So I can say that right before 3, we have
Like
overfitting.
3, because we don't have before 3. We have epoch number 1, epoch number 2, epoch number 3. So after 3, yeah.
Yes, right after 3. I'm talking about the graph because on the
Yeah.
epochs, it's like 2.5
Sure.
under, yeah. So that's what I was talking about.
Sure.
And for the bigger model, it's very noisy, but it's right after 2 epochs that we kind of have this overfitting and disorder in the model. So for this one, the best thing to do will be to keep it under 3 epochs.
Okay, so we can say that we immediately got the overfitting right after epoch number 2 for bigger model, right? That's the first problem. Well, not a problem. We have overfitting instantly. We picked the overfitting right after the first epoch, means epoch number 2. And the problem is we have a kind of a spontaneous thing. It's very noisy. It's going to be ups, down, up, down, up, something like this. There isn't any kind of a smooth approach here. So what should we choose in such cases? As we said before, we start from small and see which one fits the best with the things that we want. Anand said, to me, it doesn't look like the bigger model is accurately catching on the trends. That's totally correct. Yes, it is very erratic and starts overfitting almost immediately. Yeah, So we need always to compromise between too many capacity and a few capacity. So kind of we need to find that. But look at this one. This time we work on the bigger model and original model, but this time not on validation, but the training. Look at this one. In the original model 16, with data in hand, guys, you see that it takes time to get to 0, like after epoch number 20. But can you see that? We get that perfect answer right in epoch number 6. Look at the difference. Epoch number 6, epoch number 20. But the thing is, it's not smooth. You cannot rely on the answer because right after that, you have horrible result here. And then a little bit better. Perfect result, horrible again. You see this kind of noisy and high fluctuation that we see. The result is not that much eye appealing and acceptable. Okay, does that make sense, everybody? If you could connect to that, please type 2. Thank you, Albor. Barsa, merci. Anand, Donald. Okay, let's go to the next part. One of the things is, guys, simplicity is the best in many cases, including data science. So if you have two approaches, one of them is simpler and the other one has complex. Do you remember the example that we had from Toronto to Vancouver? Imagine that you calculate the distance based on coordination or a straight line. We use a straight line because less complex. That example a semester ago. So we have something that they call it Occam razor, and given two explanation for something, we accept the one which has most likely is going to be the one which is simpler is most likely the one that we accepted as the correct answer. For knowing more about this Occam, I have provided the wiki, but I'm gonna close my cam and let's watch a quick short video together. Just confirm, can you hear it?
Gentlemen think, philosophical concepts explained in brief in a posh English accent. Occam's razor. Developed by William of Ockham, who looked a lot like Christopher Walken, Occam's razor is the principle of philosophical parsimony. In Latin, it's entiam non sunt multiplicanda, praeter necessitatem. Entities should not be multiplied beyond necessity. What that means is we shouldn't make assumptions or postulate the existence of things that are surplus to requirement. For instance, if you have a working theory of gravity that explains why objects fall towards the center of the earth, you don't then need to say objects fall because of gravity and there are invisible demons that pull things towards the floor in order to break them. The demons in that theory don't do any work. They are superfluous, sort of extra nonsense. So we don't need them in our counterfeits. Occam's razor says cut them out. By the way, you'll see two different spellings of Occam. Occam is a village in Surrey. That's the original spelling. Occam is the Latinized version of it. Subscribe to Philosophy Tube for more from the Gentleman Thinker. Till then, cheerio!
No, I closed everything, you see. So not a just give me a second, sorry. Okay, so at least I have this one back or no. Thanks. Just forgive me for a few seconds. Okay, so let's go to this one. It says that given two explanations for something, the explanation most likely to be correct is the simplest one. And it says that simpler models are less likely to overfit than complex models. Complexity is the result of what? Having lots of layers, right? And lots of neurons to apparently detect more more things, more complex scenarios, while you can simply simplify the version by lowering down the capacity, simplifying the solution by lowering down the capacity, less number of layers, less number of neurons in each layer. By saying that, we get to another thing which says, this is just one of the ways. And the other way that we can use to use regularization for our model is to lowering down the weight. Do you remember? And now it's the time to talk about this more. Do you remember that I said before that neural network tends to work with lower numbers for neurons instead of, for instance, numbers between 0 to 255, it's the best to have 0 to 1. And now, after knowing the concept of derivatives, and we use the backpropagation, we understand that if you want to have a smooth adjustment in the weights and biases to tune our model, the best is to have smaller weights and biases. Does that make sense, guys? Again, do you remember the derivative that we learned to tune our model? Instead of working with big numbers, it's more amenable to just work with small numbers. So let's just read this. A common way to mitigate overfitting is to put constraints on the complexity of the network by forcing its weights to take only small values. But whenever your neurons contain huge numbers, how you can restrict your weights to take just small steps? It is not possible unless that you normalize your data set. What is the meaning of normalizing? Two things. It could be either, give me a sec, yeah. It could be the numbers between 0 to 1, or, well, in that case, you have divided by the maximum number that you have in your matrix, or to have numbers between -1 to +1. And in that case, the center is 0, the average is 0, and the standard deviation is 1. Does that make sense? So in that case, the weights could be manageable in the range that you expect. But let's think that, what if we want to force it separately? One of them is using weight regularization. Yes, I could pronounce it finally, which makes the distribution of the weight values more regular. What does it mean? Means that if you exceed a certain threshold, let's penalize it. We have two mechanisms to deal with that. One of them is L1, which works with the absolute value of the weight coefficient, and L2, which works with the square value of that. So this one is going to get crazy if you use huge numbers, because it penalizes you by the square of the value, not by the absolute of the value. What does it mean? It means that, imagine that if the weight is 5, right? The absolute L1 is going to be 5 multiply a coefficient that we call it alpha, which normally we use 0.001, for example. But in the second one, in the L2, we are going to deal with, if the alpha stays the same, it's going to be 25 times 0.001. Does that make sense, everybody? So this is L1. L1 and this is L2. But how this formula works, let's just see it in a few seconds. It says that this is called weight regularization, and it is done by adding the loss function. Okay, look at this one. How could you have control on the system to adjust itself? Well, by changing the loss value for sure, because that is the thing that you're going to fit to the system by giving it back to optimizer, and optimizer uses backpropagation to fix the problem. So you're going to penalize, you're going to increase the loss by adding, it says that by adding a cost associated with having large weight that penalized value to the cost function. It is something like this. Let me just show you here. Imagine that we have a loss value. So we're going to say whatever the loss was before, okay, just add this, what do we call this? The weight that we have, multiply by the coefficient that we have there, 0.001, which is alpha. Okay. The funny thing is, adding this weight is going to penalize it the way that always the loss for training, because of adding this penalty, would always be greater than the loss for testing, because we don't have that penalty. Let's look at it together. It says that L1 regularization, the cost added is proportional to the absolute value of the weight coefficient, and L2 regularization is the cost added is proportional to the square of the value of the weight coefficient. So we also call a decay or weight decay to L2 in the context of neural networks. But the real thing is how we are going to use that. It is going to apply to every single layer as you see. For instance, it says that the weight regularization is added by passing weight regularization instances to layer as keyword arguments, as you see here. So we say, for instance, L2 and the alpha is 0.001. And this is the first hidden layer. This is the second hidden layer. You can use L1, L2 here with different coefficient, but we use the same alpha for it. So we say that kernel underscore regularizer is equal to regularizer dot L2 and so on. And it says that L2 thing 0.001 means every coefficient in the weight matrix of the layer will add 0.001 multiply the weight coefficient value to the total loss of the network. Guys, in a plain English, this just simply means this. The loss is a combination of loss, old loss, plus the weight multiplying by that. So note that because this penalty is only added at training time, the loss for this network will be much higher at the training than it's going to be higher at training compared to the test time. Okay, look at this one. Isn't it beautiful? We just use L2 regularization compared to the original. You see this, it is very much smoother than any other experience that we had before, right? You may just have this comment, which is absolutely correct, and that is the loss is not as low as what we could expect in original. That is totally correct. But what if we can combine this mechanism with, for instance, lower number of inputs and combine it with dropout, which we are going to learn in a few seconds, and do these kind of things. The other way that you can apply L1 or L2 is just using regularizer dot L1 and say L1, the alpha is 0.001, or you say L1 underscore L2, the alpha for L1 is this, and the alpha for L2 is, it could be something different, okay? By saying that, we are just ready to listen to the second video. If I were in your shoes beforehand, just have a pen and paper or any taking notes device, and see what are the mechanisms that we can use to regularize our model and to tackle overfitting based on what she's going to explain to us. I'm gonna close my cam and let's watch this together.
What do you do if your model overfits? Well, regularization, of course, but regularization can be a little bit of a complicated topic. So in this video, we will talk about regularization. We will talk about what regularization is, how and why it works for neural networks, and we will go into details of some of the regularization techniques like L1, L2, and dropout regularization. This video is part of the Deep Learning Explained series by Assembly AI. Assembly AI is a company that is making a state-of-the-art speech-to-text API. If you also want to get a free API token, use the link in the description. Why do we use regularization? We use regularization for overfitting. We use regularization to fix overfitting in our neural networks or other machine learning models. So what is overfitting? Overfitting is when your model really closely fits the training data, so much so that it is not able to generalize really well to the real world. So if you look at this example, if we have only one input and we have only one output, an overfitted model would look something like this. It really closely follows all the input values and believes that this perfectly summarizes the real world, whereas that's not really the case, of course. How can you understand if your model has overfitting or not? Well, we do that by looking at the difference between validation loss and training loss. We will look at, as we train our model more and more, as we use more epochs, after some time, validation loss will start getting higher, whereas the training loss keeps getting lower and lower. And we know from that point on, we started to overfit because our model learns more closely what is being represented in the training data set, whereas it is not able to really understand what's going on with the validation data set, or generally.
Okay, so we can say earlier stop is one of the strategies that we can use.
In the real world, it is not really able to understand the pattern in the data well anymore. But how can regularization solve this? So let's take one step back and understand what happens when your model is overfitting. When your model is overfitting, it means that your model has high variance. Let's remember what variance is. It is basically how much your predictions will change on your model if the training data that you're training your model with changes a little bit. So that is how sensitive is your model on the training data that you're giving it to. Because if it's more sensitive, it means that it is overfitting. But what causes this high variance? Well, one thing that causes high variance is the flexibility of the models, because the more parameters that you have in your model, the more flexibility, the more things that you can tweak in your model, it is more likely that you will have high variance. Some examples of models that have high variance or high flexibility and thus high variance are random forests or neural networks, for example. And that's exactly where regularization comes in. Regularization is a way to limit this flexibility that the model has in hopes to avoid overfitting. This could be done in a bunch of different ways, but for neural networks specifically, this means to lower the weights of the network. You might be asking, of course, what does high weights have anything to do with overfitting? Well, let's look into that now. So let's take this example. Let's say we have this neural network. It has one hidden layer and it has 4 neurons. And in all of these connections between the neurons, we have weights. What does those weights mean? What are they signifying? So when you think about it, these weights are basically the importance of the output of the certain neuron. So if it's right after the input layer, it means the importance of this input. If it's in between in the hidden layers, it means the importance of the output of this neuron. And let's look back at an example of what it looks like when we are overfitting. If we have only one input and only one output, what happens is the model that we're training, the function, really closely follows what the input values are. So what that means is that when you're overfitting, you're exaggerating the importance of a certain input or of a certain data point. And how can you do that in a neural network? If you have a really high weights for a certain input or a certain data point, that would mean that you're exaggerating the importance of that data point. So how can you avoid this? If you lower the weights. So that's why while we're fighting with overfitting in neural networks, what we aim to do with regularization is to lower the weights that we have in the neural network. Let's see what type of solutions we have in the regularization. So there are 2 types of regularization techniques. The first one is, as we talked about, constraining the model, constraining the flexibility of the model, or you could call it, then we have fewer degrees of freedom. And the options to do that is either using L1 or L2 regularization, dropout regularization, or early stopping. That's another option that you can use. Another thing you can use to avoid overfitting, and kind of it's in also the bag of regularization, is using data augmentation. So let's go one by one on these techniques and see how they work. The idea behind L1 and L2 regularization is to adding the weights into the loss calculation or the cost function to punish the network for having higher weights. They just have slightly different approaches of how they do this. So when you're using L1 regularization, you can also see it mentioned as L1 norm or lasso all over the internet or in the sources that you're looking into. You are adding the sum of the absolute values of the weights to the loss. So it doesn't matter if your weights are negative or positive, you sum them all up using the absolute values, and then you add it to the cost. And what happens is, as a result, L1 regularization encourages the network to have weights as low as 0. And what happens when you have weights as low as 0? That might mean that some of the outputs will not even be considered in the network calculation. So it might look like this, even though you used to have 4 neurons in this hidden layer. Because this connection is now 0, this neuron is basically not really looked into yet. So as a result, you might end up with a more sparse network. L2 regularization is a little bit more different. Again, you might see it mentioned as ridge regression or weight decay all over the sources that you might find. And here what we do is we get the sum, again, of all the weights, but they're squared values. So again, you're basically making the negative ones positive, but at the same time, you're exaggerating the effects of the higher values compared to the lower values. And as a result, you're going to have differences in the weights of the network, but you're not really going to have a sparse network at the end of L2 regularization. Both of these techniques, L1 and L2 regularization, have a parameter called alpha that you need to tune. What alpha does is determines how much attention to pay to this penalty. So for L1, it was just a sum of all the weights, the absolute values of weights. For L2, it was the squared values of the weight, sum of squared values of the weight. So this alpha parameter tells us how much attention to pay to this penalty. If you make the penalty too strong, then you're going to be regularizing a little bit too hard, and it is likely that your model might underfit your model. While you're trying to avoid overfit, you might get caught in underfitting. If you make the penalty too weak, though, then your model will be allowed to overfit the data because you're not really penalizing it enough. So this is one parameter that you need to tune while you're using regularization on your network. Then we have dropout regularization. What we do here is in every training step, each neuron has a chance of P of being inactive, a probability P of being inactive. And that is called the dropout rate. Is something, again, we need to determine before we start training the network. Basically what happens is let's say we have this network, we have 2 hidden layers, and we have 4 neurons each. If we say every neuron has a 1/4 of chance of being inactive in a given step, then you might get, 1 neuron missing from here, the first one, the second one, again, some neurons missing from the first and the second. You might have less than 1/4 of all the neurons missing, or more than 1/4 of all the neurons missing, of course. But on average, you're always going to have 1/4 of neurons missing while you're using dropout regularization during training time. And one little trick here, one little thing that you need to understand about dropout regularization is that when you're training, some nodes or some neurons are going to be missing, but when you're testing, they're not going to be missing. So as a result, what you need to do is to use something called the key probability, which is 1 minus the dropout rate. And you need to multiply your inputs with this key probability, because if you think about it, because we are missing dropout rate amount of, or in this example, 1/4 of all the neurons on average during the training steps, we are basically going to be receiving 3 inputs. But for the test time, we are going to have all of our neurons, and then we're going to be receiving 4. So that's why we need to multiply our inputs with the key probability to make sure that the model is able to predict correct things and it's not really rigged in any way. And the next one we have is early stopping. We've seen this graph before. The more you train your network, the less the training loss is going to get. But after a while, validation loss is going to start getting higher. And as we said, that's the point we start overfitting. What you can do with early stopping is to stop it at that point and say, okay, after 30 epochs, my network starts overfitting. So I'm just going to stop the overfitting process. Though I have to say, this is kind of a controversial technique. Not everyone agrees that this is a good way of dealing with overfitting, because what we want to do is we want to train our model, make sure that it converges to a solution, and then have a separate process on top of it to deal with overfitting rather than stopping training early. Because combining these two processes, namely training and mitigating overfitting, will cause further confusion down the line. And the last technique that we have is data augmentation. So it's always a good idea to feed more data into your network, feed more different data into your network, but that might not always be possible for you. You might simply not have enough data, but especially if you're working with images like these, let's say you are trying to understand or find dog faces in images, but you always have dogs sitting in a certain position, really straight, 90 degrees to the camera, and looking directly into the camera. But you want your model to tolerate other pictures of dogs. You want it to be able to generalize to the real world. So what you can do is to flip or rotate or do other transformations to your images to basically have a more enriched training data. Or if you want your model to be tolerable to the changes in exposure, saturation, or even just colors in general, then you can apply some other transformations to your data, increase the saturation, increase the hue, invert the colors, make it black and white, and then feed all of this data into your network so that it will be able to still recognize that this is a parrot, even if the colors are completely off. And that's how data augmentation will help us regularize and overcome overfitting. All right, so that's it for regularization. I hope everything was clear. If you like this video, please give us a like and maybe even subscribe to be one of the first people to know when we publish a new video.
Okay, guys, if you can hear me clearly, please type 1.
And if you have any questions or comments, I will.
No, we don't. Thank you, Anand. Where's Al Gore? Hey. Donald. Just woke up. Don't be that much honest. Okay, so let's go to the next part together. I try to finish as quickly as possible so Al Gore can have more rest. And I know that, guys, close to the end of the semester, we all have sleep issues. So hopefully these final steps would be passed as successful as possible. Okay, let's say dropout. The instructor in the video just quickly explain what dropout could be, but let me tell you, Jeffrey Hinton, he was the he's the father of deep learning. He said that he was the one who just supported this approach, saying that dropout applies to a layer consists of randomly dropping out or setting them to 0. Let me just show you before we go any further. So it means that imagine that you have something like this, a matrix like this. Then you are gonna zero out some of those random cells like this one, this one, this one, huh? And how we are gonna do this, look at this one. It says that the layer output multiply random. What does it mean? Let me show you. Imagine that okay, you can see this. Imagine that we have something like 0.5, 0.3, 0.1, and 0.2, something like this, right? So we say that this one is equal to the same thing, which is going to be 0.5, 0.3, 0.1, 0.2, multiplying by the random values between 0, as you see here, 0 and 2, not including 2, so it's going to be just 0 and 1. In random integer numbers, the minimum is 0, the maximum is 2, not including 2, so it's going to be 0 and 1. And the size would be exactly the size as we have in the original vector or matrix. So in this case, it's going to be, sorry, just give me a second. Which is going to be this one. Because it is random, it could be, guys, 1, 1, 0, 0, or it could be 1, 0, 0, 1, or even it is possible to have, because it is random, it could be 1, 0, 1, 1, something like this, right? But let's just imagine that it is like 1, 0, 0, 1, huh? So the result of that would be something like 0.5, 0, 0, and 0.2. But can you see this here? What is the overall sum of this vector? It's going to be 5, 8, 9, 10, 11. So it's going to be 1.1. While the output of this one is going to be what? It's going to be 0. I'm sorry. It's going to be 0.7. Well, I'm not lucky very much, but it is almost like half of the original because we used 50%. Yeah, that's great. But I'm saying that this is half of the. So we are not going to apply this dropout. We are not going to apply this into our testing data. We just work on training data. But the problem is in that condition, what happens? We almost, as I'm saying that almost, if it's 50%, we have 50% of the weights that we had before of the values that we had before, while the testing would stay the same. Okay. So that is the question. What should we do here? One of the approaches is, okay, you used Reza 50%. Let me do one thing. Let me divide this by 2, the weights that we have. For instance, if we have a matrix that contains 2, 5, 3. I'm just fabricating numbers. Let's just have 2 rows. 1 and 6 and 8. And then let's just say the result would be, sorry, I'm just going to use 1, 2.5, 1.5, and then 0.5, 3, and 4. Does that make sense? So we converted that into something half of the size because we want to adjust our testing to the, what do we call it? To the training that we have. Guys, is it clear? Oh, sorry, you don't. Guys, is it clear? My apologies. Yeah. So this was the original testing, and then I just divided by 2 to make these two like training and testing in the same scale. Guys, if it is clear, would you please type 1? Thank you very much. Let's go to the next part together. So it says that one of the ways is to say, for instance, because we used 50%, let's lower down the test values by multiplying by 0.5. What could be the other solution if you don't want to touch the test, guys? Any idea? It is very simple. Just take your guess. Instead of dividing the test by 2, you can do what? You can multiply the train by 2, right? Do you accept that? Instead of dividing by 2 in the testing, you multiply the training by 2. Does that make sense? It's going to give you almost the same result. Means that instead of having 0.5 over there, we are going to have the results would be something like this. It's going to be 1, 0, 0, and then 0.4. It's going to just, it does almost the same thing for us. Look at the explanation in the book. It said that, hey, if you work and say, let's have 50% of the values, convert 50% of the values into 0, the thing that you can do would be this one. You can just say, divide the final things by 0.5. What does it mean, guys? It's a simple math. When it says that whatever the value is, what did it say? Okay, it says that for instance, layer divided equal to means that whatever it is x, instead of saying just copy and paste this one, it's going to be easier to work. Sorry. Okay. If you say layer divided by, guys, just pay attention to this. If I say x divided by 0.5, it is equal to, does it show? here it is. It is equal to saying x over 1 is divided by a 1 over 2, so it's going to be exactly like multiplying that, so it's going to be 2x over 1. That's it. So the simplest way of saying this is when you zero out, when you drop out half of them, multiply the rest of the weights by 2 to compensate the loss values that you had. If it is clear, please type 2. If not, layer output, let me just say it. Okay, here it is. Layer output divided by 0.5 and place it into its place again means that layer underscore output divided by 1 divided by 1 divided by 2. So it's going to be 2 times layer underscore output. That's why I said it. Okay. So look at here. First, you drop out in order to keep the scale similar to what you could see in the test data. Finally, you are going to say multiply 2. This technique may seem strange and arbitrary, but what happened, actually, it says that Jeffrey Hinton went to the bank and saw that tellers keep changing. And he asked that, okay, why that happens? They said to avoid conspiracy. So they group up and they try to do something, okay, in terms of fraud and so on. So not to have a kind of gang, or let's just keep changing the staff. That strategy to eliminate the conspiracy was the initial idea of dropout. And he said, in that case, maybe there are some patterns that in a sort of mysterious way, they find each other and they recognize a pattern that are very much special for the data in hand and not general for unseen data. In that case, what if I cut that relationship by just taking those values out? So this made me realize that randomly removing a different subset of neurons on each example would prevent conspiracies and thus reduce overfitting. And it said that you can simply, that's a good thing in Keras, you can say, hey, do the dropout. You don't need to write even a single line of code to implement that. It's already there. You just use that. Look at the sentence. It says that in Keras, you can introduce dropout in a network via the dropout layer, as you see dropout layer, which is applied to the output of the layer right before it. So we are going to apply to an output a layer right before that dropout. So this two, and I could say these two, but I just took the last two to show you this dropout, how it happens on the layer right before it. Look at the result there. Guys, the beautiful thing about that dropout is not only it gives you similar or better result in terms of the lower loss, it is less noisy, right? It is less noisy and it is smoother, and it almost happened at the same time. So it's not like the one that we saw in regularization. It doesn't fit the set. So what if we combine all these techniques together? That would be awesome, and it's gonna give us the best possible result. And it tries to recap all these techniques. It says that to recap, we could get more training data intuitively. Whenever you have more data, more general concept, you can just get. Reduce the capacity, reduce the number of layers and neurons in each layer, add weight regularization, L1, L2, and add dropout, right? By saying that, we get to a kind of recipe that we would have in all workflow of machine learning, specifically in deep learning. Okay, so guys, how about this? Let's have 2-3 minutes break. I'm sorry, I need more warm water. And after a short water break, we're gonna continue. Sorry. So if you can hear me clearly, please type 1. Thank you, let's see. Track me. Unlock me. Okay. So let's go to the next part. The universal workflow of machine learning contains these steps. It says that the blueprint ties together the concept you have learned about it in this chapter, contains problem definition. What is the problem definition? First, what is your major question? What problem you want to solve with data in hand? And does the data set you have bring you to the labels that you want? Does the labels, do the labels already exist, or you need to annotate it yourself, annotate them yourself? The evaluation, do you have any mechanism to dynamically trace and monitor the result that you have? And feature engineering, what are you gonna do with the numbers that are not in the same range? Or what are you gonna do with null values? And how about dimensional reduction? Selecting some features, I'm selecting some others. And how are you going to deal with overfitting? So first thing is, the first question is, what will your input data be? What are you trying to predict? You can only learn to predict something if you have available training data. Guys, it's not possible to predict something that you do not have already the data about, right? It just can find similar patterns and tell you that, okay, you know what, I've seen something similar to this, so it could be the output. So data availability is one of the challenges that we have, unless that you are rich and you can just hire some people to collect data for you. So that's one of the challenges, right? And what type of problem are you facing? Is it binary classification, multi-class classification, multi-class, multi-label classification, regression? But which type of regression, even if you want to say, is it scalar regression, vector regression, what, right? Which one could be? Something else like clustering generation or reinforcement learning could be the answer to your domain of the data. Identifying the problem type will guide you to choose the model's architecture. What are the model's architecture like? What are the loss functions, activations for the last layer, optimizer. Optimizer most of the time we use just Ram's prop, but in rare cases Adam. So and so on. So it's gonna help you. So next page and in next 2 pages, you're gonna have that cheat sheet. Let's see. Identifying the problem will guide you, yes. And we say that you can't move to the next stage until you know what your inputs and outputs are and what data you'll use. Be aware of the hypothesis you make at this stage, guys. This is that important that we see similar sentence in 3 pages from now. It says that you hypothesize that your output can be predicted given your input values. So it means that you can get to output starting from the input, right? And hypothesize that your available data is sufficient informative to learn the relationship between input and output. Means that yes, it can bring from X to Y, but I do not have enough number of samples for such a case. So what should I do? So getting from X to Y is one issue. The other thing is, do I have enough information to get? So I can, but it is possible, but I can do that unless that in the case that in condition that I have something like 1,000 of records, right? It said that if you're trying to predict the movement of a stack on the stock, Guys, is it possible? This is one of the problems that most of the time people have. Is it possible to rely on the history? Can you predict tomorrow's Bitcoin price based on all the data that you have in the history of Bitcoin since the day one? Yes or no? So Donald said no. Alex said no. Guys, if you can predict 1 minute from now, you can become the millionaire in 1 minute, billionaire in 1 day. We don't have that knowledge. Unless that you have relationship with Elon Musk and know that what could be the next tweet that he's going to. Yeah, if you know that Elon Musk is going to tweet something against Bitcoin or not. So these are parameters that we don't have, right? That is one problem. We can't formalize all the parameters that engage in something like stock market. That's one problem. The other thing is, it says that one class of unsolvable problems you should be aware of is non-stationary problem. Like what? Some of the things change during the time. Like what? Imagine that the winter jacket. Can you predict how many winter jackets you might need based on the data that you have in August and predicted for December? It's awful if you do that, right? So one of the thing is, actually, yes, that's one of the, Anand was kind enough to share one of the approaches. One of the approaches is we use the most recent data for such cases. That's one approach number one. But the other approach is we go back to last year and see how many, for instance, winter jackets we sold in December. You know what I'm saying? So similar time period last year. And we see that, for instance, if in general we have a kind of progress in selling the stuff, imagine that we are in Hudson Bay. We want to see if we have any progress, if you had any progress in general, so we can just estimate that we sold almost 7% more products. You could expect that we need to have 7% more winter jackets, something like this. But again, that's not enough because there are some other parameters. Did we have the same winter? Was it milder last year or severe cold last year? We need to consider those things. So these are the other factors that could impact the sale that we are going to have this year. So it says that the big issues and that the kinds of clothes people buy change from season to season. So clothes buying is a non-stationary phenomenon over the scale of a few months. What are you trying to model changes over time? In this case, the right move is to constantly retrain your model on data from the recent past. That is something that Anand said. Or gather data at the time scale where the problem is stationary. For this problem, for instance, for a cyclical, periodical problem like clothes buying, a few years worth of data will suffice to capture seasonal variation. So let's go to the next thing. It says that keep in mind that machine learning can only be used to memorize patterns that are present in your training data. Means that you can only recognize what you have seen before. You should have similar patterns, otherwise you can't do anything. It says that to control something, you need to be able to observe it. What does it mean? We need to have a metric an index to show if we are successful in something or not. For machine learning, for deep learning, that matrix is the loss, how far from the correct answer we are. If we use a balanced data set, a balanced classification problem means that the number of possible, I'm saying that the number of possible positive and negative are almost the same. Then accuracy or rock up could be the to-go options. But when they are not balanced, like we have 10% cats, 90% dogs in our data set, then we should go and use precision or recall. How about using multiple classification? In that case, when we have multi-label, multi-class classification, we use mean average precision. And if there is a problem that is not one of the common problems, you might say, I need to create my own loss function. Let's see, guys, you remember, one of the thing is, it says that deciding on an evaluation protocol. Evaluation here means not testing, means that dynamically checking the performance of your model. So we have three different approaches. One is holdout validation. You know that, for instance, you have 100,000 samples. You put aside, you hold out 20% of it, which is 20,000, and you train based on the remainder, which is 80,000. But when you finish your job, the final step would be training your model based on overall 100K. Does that make sense? Guys, if it is clear, please type 2. Thank you. What about if we have limited number of, samples, and then k-fold, take 1/3 out, train based on the 2/3, use that 1/3 as the validation, then bring it back, take the second 1/3 of it, and then do the same thing with the leftover, train on the 1/3 at the beginning, 1/3 at the end. Do something like that. You're familiar with that. The other thing is, if you have limited number of records, samples, but you need high precision, in that case, you need to do that k-fold out, k-fold validation, and do it several times, and that is iterated. For instance, you're going to do 10 multiply 3-fold validation. It's going to take quite a good amount of time, but it's precise compared to k-fold. Sorry. Okay, preparing your data. What does it mean? You remember I talked about it. What you're training on, what you're optimizing for, and how to evaluate your approaches. You're almost ready to begin training the model. The first thing, you should format your data in a way that can be fed into a machine learning model, and that is turning your data into a tensor. Guys, you remember that the first thing that we had, one of the first examples that we worked on was this example, right? The 784, but before that, you remember the size of the samples was 28 by 28, 28 rows and 28 columns. We transform it, we reshaped it, or as correctly we can say, we flatten the data into 28 times 28, which turns into 784 neurons, as you see here. So that's the first thing that we have to do. We change the data into a tensor and vector. The values then should be either between 0 to 1. I'm not saying that without this range it's not going to work. It works, but all the story that we talked about. Neural nets work better with small numbers, weights, biases, tuning them, weight penalty, everything. And the other thing is between -1 to 1, the center in that case is going to be 0, and the standard deviation would be 1. So it says that if different feature takes values in different ranges, you need to normalize it. The example was Boston housing. You may want to you may want to do some feature engineering, especially for small data problems. But there's a new concept, and it is statistical power. I want you to spend a few seconds and see if you can find statistical power. What is a statistical power? Okay, Al Gore, can I ask you? Are you there? Still there? Okay. Imagine that I show you a picture of a number, right? Imagine that I have one number on this page, 0 all the way to 9. And you want to, let's just practice that. Okay. Now I wrote one number. Can you guess what that number could be? You could just guess one number. How do you know that? It was 7. Both of you, guys, you ruined the whole example. Somebody should say 3, somebody should say 5, somebody should say, both of you said the correct answer. Guys, I'm talking about normal cases. In normal cases, the chance that you say correct answer yes, you're right. Next time I'm gonna pay attention to that. I'm gonna choose any number apart from 7 or 3. So look at this one. Normally, if I say that there is a number, the chance that you say it correctly, forget about this experiment that we had, is gonna be 10%, right? Guys, if I have a number and I ask you that, what is that number? The chance that you say the correct one, it's gonna be 10%. Any algorithm that you write that can increase that chance over that 10% is acceptable. It means that it does something. It's not gonna be the perfect for all the cases, but it does something. It's better than nothing, better than random. And it's exactly what we are talking about. So it says that in the MNIST digit classification example, anything that achieves an accuracy greater than 10% can be said have a statistical power. In IMDb, which was positive or not positive, that ratio was 50%. What does that reveal? Let's just say, flip the coin, positive. No, it was negative. The next one, positive. Yes, it was right. You know, so to score our improvements so that we can create a better model. Means that we can call, you remember, Anand, that's a good question. You remember that we said, first, let's define a problem statement. And for that problem statement, do you have an input that brings you to the output? That's the first question. And if there is a way, do you have enough resources to go from A to B, from X to Y, right? If you can get, by any of the algorithms that you choose, anything above the statistical power, means that good job, you're on the right track. Huh? So it says that, remember that you make two hypotheses, and please pay attention to this one. This is something that I promised you 2-3 pages ago, that we are going to see this pretty soon again. You hypothesize that your outputs can be predicted given your input. So there is a way from X or X's to Y's. And the other thing is, you hypothesize that the available data is sufficiently informative to learn the relationship between inputs and output to discover the patterns. The other thing that I see from Anand said, I see. So it's a way to score our, yeah. And Ali said that it's a way to draw a more accurate conclusion. True. All right. Anand said, all right. So I could potentially compare it to some test. In medical test methodology, I'm not sure about that. I'm sorry, my knowledge is very limited. Let me just see if I know it in my native language. First, did I pass that test anyhow, anywhere? I don't think that it is a it's like pseudo drug, pseudo medicine kind of thing, right? I can't find any relationship between these two. My bad. Medicine has to do better than doctors telling you this medicine will make you healthy, but it is a fake pill. Okay. There was one class that I was in, and they talked about this. For instance, imagine that we have a medicine, and we have 50,000 patients, and we give them all correct things into that portion. We have a test group that we give them a pseudo medicine, and we say that they are the same. So those people, they don't know that they are not using the correct, yeah. And then we see that if the percentage of the people that they use the medicine and the correct medicine and they get better, then it shows that it is working. And if it is lower than that threshold for and it was almost the same as those people that they used pseudo medicine there, yes. That's a good thing to know that. Thank you, Anand, to bring that. I'm gonna just search, and I can bring more meaningful example for the next session. So look at this one. Remember that you make two hypotheses based on what I said. The first is if the input brings you to the output, and if you have sufficient number of samples for that. And assuming that things go well, you need to make 3 key choices to build your first working model. Guys, do you remember if it was a binary classification like cat and dog or positive, negative? What is the last layer? What is the last layer activation function? If you remember. Binary classification, it gets closer. Zoom out further. Zoom out further. Oh, thank you. Okay. Guys, what is the last layer? What is the last layer classification? Sorry. Activation. If it is binary, it's gonna be sigmoid. It's gonna be either sorry. It's gonna be either classifying to 1 or 0. You remember that? It's gonna classify to either 0 or. What if we have this one, like MNIST? What is the last layer activation? You remember that? For here? Donald Bravo. Softmax. Right? What if we have regression like the Boston housing? What is the last layer activation? Anyone remembers? We don't have any activation for regression unless that it is between 0 to 1, which we are going to use on the same sigmoid. Because if it is regression and you want to predict the price of the house, you want not to limit it into any range, right? It could be any number. So look at this one. It says that the last layer activation is established useful constraints on the network output. For instance, IMDb classification, we use sigmoid. Regression, you don't use any last layer activation and so on. For loss function, it really depends. If you are using, for instance, one-hot encoded, like the example that we had in Reuters and IMDb, we use cross entropy, categorical cross entropy. But if you don't use one-hot encoded and you have integers like what we had in MNIST, in that case, you use the sparse categorical cross entropy. And if you have something like a binary or vector regression, in both cases, you simply use binary cross entropy, right? Sparse categorical cross entropy. Lovely, Anand, bravo. So the loss function, it talks about the possibilities, and for the optimization, we use mostly ramsprop. It's a kind of to-go thing. So it says that we use ramsprop. Rarely we use Adam. It's old-fashioned compared to ramsprop. So the loss function, after all, needs to be computable given any mini batch of data. Guys, what does it mean? It means that whenever you want it, look at this one. It says that sometimes there is no way to tune a metric into a loss function, because loss function, after all, need to be computable given only a mini batch of data. Ideally, if you just give one picture, it should just start working. And must be differentiable. Why it needs to be differentiable? Because you need to calculate the derivative and pass it to the you pass the differentiable value to the optimizer, and optimizer goes to the backpropagation. If it is not differentiable, then you can't use backpropagation, right? Sometimes we can use different metric like ROC-ONC, and in that case, if the classification works the best, this is going to work approximately the same way as ROC-ONC. So there is a chance that they don't have exactly equal relationship, equality relationship, but proportional relationship or counter a relationship. So the one goes up, the other one goes down. So we can just judge those metrics. This is what I told you always. If you have binary classification, the last layer should be sigmoid. The loss function binary cross entropy, multi-class single label, it's going to be softmax. You remember that for MNIST, and categorical cross entropy would be the loss function. If you have multi-class, look at this one. This is funny. Multi-class, multi-label classification. It looks like binary classification, sigmoid and binary cross entropy. Look at this one. If you have regression in the range of 0 to 1, you can use again sigmoid, and you can use binary cross entropy. Yeah, you also can use MSE, but I'm saying that for 3 of these models, sigmoid would be the last layer activation, and you could use binary cross entropy. For regression to arbitrary values like Boston housing, you don't need to use any. You shouldn't actually use any activation for the last layer, and mean square error is what we use as the loss function. So it says that scaling up, developing a model that overfits. You remember after all these steps, knowing that the data brings us from X to Y, make it appropriate, taking care of the lost values and the missing values and so on, and do the engineering that you need, picking the architecture for your model. Finally, we get to the real problem, which is going to be tackling the overfitting. So let's say that once you've obtained a model that has statistical power, means that works better than random result. The question becomes, is your model sufficiently powerful? So remember that the universal tension in machine learning is between optimization and generalization. You know that better than me now. The ideal model is one that stands right at the border between underfitting and overfitting. But the problem is we cannot get to the number of epochs or something and say, okay, stop there, unless that you pass that border once. So between under capacity and over capacity. To figure out where this border lies, first you must cross it. And then say, you remember that earliest stop in the number of epochs, that's when we saw, for instance, in 30 epochs, we had a benchmark for validation for all those epochs. And then we said, after 7, we just waste the resources. 7 was enough. So add layers, make the layers bigger, and train for more epochs. You must develop a model that overfits, and then stop it in the border. How we can make it overfit, to add layers, to make layers bigger, and to train in more number of epochs. And then it says that when you see that the model performance on the validation data begins to degrade, that's the place that you have to stop. You have achieved overfitting. And you remember that for regularization, to regularizing your model, we had these approaches. This step takes most of the time. You need to add dropout, Jeffrey Hinton banking staff, you remember? Try different architectures, like how about 2 layers, 16, 16, how about 3 layers, 256, 256, 256. You need to try many things to just realize which one works the best. Adding L1 regularization, L2 regularization. And try different hyperparameters. This one is pretty close to this one. It says that add or remove layers, different architecture. This, apart from the layers, it talks about the possibility of using, guys, architecture is not just the number of layers. It's not only hyperparameters. It also contains the number of batches, the number of batches that you want to, the number of elements in a batch, mini batch size, also the number of epochs and so on. So also different hyperparameters, such as a number of units per layer or the learning rate of the optimizer. And optionally, you iterate on feature engineering and say, okay, these first 20 columns have the most, I'm just fabricating, they are the most important columns. Let's forget about the rest of 480. Out of 500 columns, you pick just 20. Or no, you're going to just generate a new columns, and then you say, these works better. But you shouldn't overdo these steps, because whether you want it or not, because you dynamically check it with validation data. So validation loss and validation accuracy, you may leak some information to the validation, and you make the data set get overfitted on validation. And that's not something that can be helpful for us. Once you develop a satisfactory model configuration, you can train your final production model on all the available data. So training and validation, and evaluate it on the last time. Means that you put aside 80% for training, 20% for validation, and then you did all those things. The final time you're gonna work on what? 80% plus 20%, the combination, the concatenation of the overall data. So if it turns out that the performance that you have on the test data is way lower than the performance that you could see on the validation, it shows that your validation didn't work the way that you expected. Means that you need to use, instead of, for instance, hold out validation, you need to use cross validation. For instance, k-fold cross validation, 10-fold cross validation, or iterated 10-fold cross validation. It says that it turns out that the performance of the test set is significantly worse than the performance measured on the validation data. This may mean either that your validation procedure wasn't reliable after all, or that you began overfitting to the validation data while tuning the parameters of the model. In that case, the best is the more reliable evaluation protocol would be using iterated k-fold validation instead of just hold-out validation. We conclude the chapter by summarizing all those steps into these 6 bullet points. So define the problem at hand and the data on which you'll train. Collect this data, annotate it if the labels are not available. Choose how you'll measure your success. What is the indicator that shows, define your loss if it is not there. And if it is one of the classical problems, just use binary cross entropy, and so on. Which metrics will monitor on your validation data, splitting the data. And it says that determine your evaluation protocol. So do you want to have holdout validation, k-fold validation, or iterative k-fold validation? Which portion of the data should you use for validation? And develop a first model that does better than a basic baseline, and a model with statistical power. So first get to the cutoff to that statistical model, and then develop from there. And develop a model that overfits and then stop before overfitting. Regularize your model and tune its hyperparameters based on performance on the validation data. a lot of machine learning research tends to focus only on this step, which regularizing the system, but don't forget that we have a bigger picture, and that is finding the correct labels for our predictions. By saying that, we have already covered everything that I designed for in this session. Next week, we are going to get to chapter 5, part 2, which is going to be a practical intuition. We are going to watch one video, actually, but the other video is amazing. I've just left it there for you. Please just watch it at your convenience. The second one is 30 some minutes. We can't watch it in the class. The thing is, we start working on a pre-trained, well, let's just say first, for the first time we work with the concept is convolutional neural nets, the way that we call it convnet, not the old-fashioned artificial neural nets. Let me just tell you one thing now. Till this moment, what we actually did was using artificial neural nets, but convnet and max pooling are the things that we are going to start using in chapter 5. We get to a real practical problem statement, and we are going to start hands-on in the coming lab that we have. Apart from this, I tell you that I've already opened the assignments number 3's folder. Most of the concept that you need will be covered in next 2 weeks before the due for the assignment. So hopefully you're gonna enjoy working on it. If you work ahead of time, whenever I explain the content, you're gonna enjoy more. But if not, you can just leverage the content of chapter 5 to resolve the issues in your assignment. If there's any concern, any question, anything that you need to say before we close the session, please let me know. So Algor, Ali, Alvaro, Anand, Donald, Erdal, Erica, Luis, Parsa, and Sabrin, thank you very much. Have a wonderful evening, and thank you, Luis. I didn't see you, sorry. Have a good one. Take care of yourself, and see you next week. Ciao.